Okay, good day to everyone. We will now proceed with module 1 of quantity surveying. So this will now be all about concrete. So what is concrete? Concrete is either plain or reinforced. So by definition, plain concrete is an artificial stone that is a result of mixing cement. Okay, cement is the powder. We also have fine aggregates, which we commonly call as your sand. In coarse aggregates, your gravel, and one vital composition of the concrete for the hydration process to complete is water. Again, the hardening process is what we call hydration. So the conglomeration of these materials producing a solid mass is called plain concrete. Okay? Reinforced concrete on the other hand is a concrete with reinforcement properly embedded in such a manner that two materials act together in resisting forces, because concrete is very brittle. Therefore, as far as tension is concerned, it is really very, very weak. So here, take a look at this beam right here. Okay? So the beam right here has an obvious bending. This is already a failed beam. So what caused this one? It is due to bending because it is carrying a very heavy load on its back. Okay? And it is also carrying its own weight, which is also very heavy. That's why it failed. Now, the upper fiber of this concrete is experiencing compression. Okay? When you, of course, bend a beam right here, the upper part experiences compression, just like in the beam here, it's compression, and on the lower fiber, it is already stretching. Therefore, it is already resisting a tensile force. Okay? As I was saying a while ago, it is really very weak in tension. That is why they are reinforcing it with steel bars. Okay? So we have a photo here of a plain concrete and a reinforced concrete. We also have different types of concrete used in construction, but we are not really concerned in the details of the types of concrete. But let's just take a look at these types of concrete. So ordinary Portland cement. Okay, we also have rapid hardening Portland cement, which is preferred when high early strength concrete is desired. So the hydration of this is just faster than the ordinary Portland cement. So we also have blast furnace or sulfate cement used on concrete structures designed to resist chemical attack. Okay, this is most commonly used in labs and plants, or even the concrete that is inside the water. Okay, we also have low heat Portland cement used for massive sections designed to reduce the heat of hydration. So if we are observant enough to play with concrete when we are young, okay, the temperature of Portland cement or the fresh concrete is way higher than the temperature in the surroundings. So that is also a part of the hydration process. So imagine pouring a very large amount of concrete, okay, for example, in the construction of large dams, it will really affect the temperature in the surroundings, which will be very difficult for you to work in. So they are using low heat Portland cement. We also have Portland Pozzoland cement with low hardening characteristic concrete. And we also have high alumina cement, also known as aluminous cement or cement pundu. Okay, we have main compositions of cement. We should also be careful with our terminology cement, because sometimes we interchange concrete to cement. Okay, so if we say cement, we are just referring to this powder right here. that is the cement. So if you mix water with it and you mix it thoroughly until it becomes a paste, that is called a cement paste. But that is not yet a concrete. Okay? So we always refer to our floor as cemento in Tagalog, but we should call it as concreto. Okay, or concrete. So here are the compositions of cement. We have lime, silica, alumina, iron oxide, magnesia, and sulfur trioxide. That is in cement alone. So if you want to make concrete, just put sand, water, and gravel. For coarse aggregates, the sizes depends upon the dimensions of the concrete member, particularly the spacing of the steel bars reinforcement, or as specified. Okay, so if we take a look at this form right here, this will now be a column which is ready to be poured on, okay, with concrete. Now, if the size of your gravel will be very, very large, of course, the concrete will not be uniformly distributed all around this column right here. All of the gravel will be stuck in the spacing, okay, that will not allow all of the concrete to flow smoothly. So, good practice demands that maximum size of coarse aggregate should not exceed 25% of the minimum thickness of the member structure, nor exceed the distance between the reinforcing bars and the form. So, of course, the spacing of the rebars, okay, should also be considered for the concrete to be poured smoothly. We also have principles of concrete mixing. We should have the following requirements that we should meet in producing your concrete. Okay, we should have workability, okay, which we will define later. We also have the strength of the concrete, the durability, and how economical the concrete mix is. Okay, the proportion that will be finally adopted in concrete mixing has to be established by actual trial and adjustment. Processes to attain the desired strength and quality of concrete required under the following procedures. Okay, we have the water to cement ratio. Okay, that is the first to be determined at the very first hour of mixing to meet the requirements of the strength and durability. Okay, we also have to determine how much water or how much cement we should pour in the concrete mix. And we also have the cement to aggregate ratio is then chosen and established to satisfy the workability requirement. So what is workability? That is the ability of the fresh concrete to fill all the voids. Okay, that is what I was telling you a while ago. These are the spaces, okay, that we call voids. Okay, the spaces under this form right here is what we call the voids. It should be filled easily. Therefore, we should produce a concrete that is workable, or concrete mix that is workable. Okay, between the steel bars and the forms without necessarily exerting much effort in tamping. Okay, we are also using a steel rod to tamp all of the concrete mix to distribute all over the voids. Workability is also, how do you define this in simpler term? It is, if your concrete mix is workable, meaning you can also mix it easily. Unlike if you are mixing a very dry and not much water is added on the concrete mix, that will be very, very hard to mix, most especially manually. We have here ACI requirements for concrete, which will now be self-explanatory. We also have concrete mixture classification. We have the designed mixture and the prescribed mixture. Okay, so let me just simplify this concrete proportion table. So this is the basis. Actually, this is the basis of ordering the amounts or the quantity of materials that you should get in a hardware. Okay, so for a specific amount of concrete, this is the basis, okay, for you to avoid ordering too much or ordering less. So let me just explain to you. So this concrete proportion table is really intended for 1 cubic meter of concrete. Okay, so for example, in class AA, by the way, class AA is the strongest, okay, in comparison to the other classes, and C is the weakest, or not really the weakest, but it has the least strength in comparison to the other classes. So class AA, the strongest, and this one will have the least strength. You can also use this proportion right here, but I will explain that later. Okay, so this will be the more important one compared to this one. So let me try to explain this. So in 1 cubic meter of class A concrete or class AA concrete, you should put 12 bags, okay, of a 40 kilogram bag cement. Okay, because you have two options in ordering cement. There is a bag that has a 40 kilogram bag or a 40 kilogram cement and a 50 kilogram. But this is what is commonly ordered because I think it is more available than the 50 kilogram. Okay, so let me just try to repeat that. In 1 cubic meter of concrete, okay, if you are making 1 cubic meter of concrete, class AA, you should put 12 bags of a 40 kilogram bag cement and 0.5 cubic meters of sand and 1 cubic meter of gravel. Okay, so try to imagine this. If you are adding gravel and sand, which is 1 cubic meter and 0.5 cubic meters, would it be 1.5 cubic meters? No, because if you are making 1 cubic meter of concrete, it will fill all the voids that is in between the gravel. Okay, how about water factor? You will use 6 gallons per bag of cement. Okay, you will understand this further later in your problem. Okay, so let's try one problem. A proposed concrete pavement has a general dimensions of 10 centimeter thick, 3 meters wide, and 5 meters long. Determine the quantity of cement in bags and sand and gravel in cubic meter and water in gallons. So this will now be the application of this table right here. So let me explain to you. So what is the volume? Of course, we should estimate the volume. Let us compute the volume, that is length times width times height, or the thickness times width times height, or it really depends on how you label your dimension. So this will now be 0.1 because the thickness is 10 centimeters. That is, when converted to meters, that is 0.1 meters times 3 meters times 5 meters. All in all, that is 1.5 cubic meter concrete. Okay, if they said that it should be a class A concrete, how many bags should be present in the concrete mixture for you to make a class A concrete? So if we go back to the table right here, in class A concrete, there should be 9 bags of a 40 kilogram bag of cement. Okay, I think this will already be constant per cubic meter. So 9 bags, 9 is to 0.5 is to 1. Okay, So let's try that. So number of cement, if we are computing the number of cement that we should order, okay, we will simply multiply 1.5 cubic meters times 9 bags, because this is what is specified in your table, 9 bags, okay? 9 bags of cement per cubic meter concrete, therefore 1.5 times 9 will be 13.5 bags. Therefore, we should order 14 bags of cement, because we cannot really order half a bag of cement. Therefore, we should round that up to 14 bags of cement. Okay? How about the sand? You will just multiply, okay, the quantity in cubic meters multiplied by 0.5 cubic meter sand per cubic meter of concrete. Okay, let's go back to the table again. In 1 cubic meter of concrete, there should be 0.5 cubic meter of sand in 1 cubic meter of gravel. Okay, so we will simply multiply that by 0.5. Therefore, the answer will be 0.75 cubic meters of sand. Okay, how about gravel? So the proportion of gravel to the concrete is 1:1. Therefore, if you are making 1 cubic meter of concrete, you will just multiply it by 1, because you will need 1 cubic meter of gravel per cubic meter of concrete. Therefore, you will need 1.5 cubic meters of gravel. Okay, and the volume of water, as it is specified a while ago, that should be 6 gallons of water per bag. Therefore, you will multiply 6 by 14 to get 84 gallons. Okay? But I think it is more correct if we should multiply 6. Okay, we should multiply 6 by 1, or it should be 13.5. Okay, because 13.5 bags are poured to this. But it is just rounded up to 14 bags, because there is no 1 bag or half bag of cement. Okay, so what is the answer for this? 6 times 13.5 will be, I think, 81. So I think it is more accurate to use this proportion. Okay, now if we summarize all of the quantity, you ordered 14 bags and 0.5 cubic meters of sand and 1.5 cubic meters of gravel and 84 gallons of water. So 14 times 240, because this is the price of per bag of cement. So this will be 14 times 240. So in cement alone, you already spent 3,360. Okay, and per cubic meter of sand, that is 900, but you only needed 0.75 cubic meter. So that is just 3/4 of a cubic meter. Okay, so next, 1.5 cubic meters of gravel. That is 1,000 per cubic meter. That is why if you multiply that 1.5 to 1,000, that will now be 1,500. So here in water, so per gallon of water, it is estimated to be 5 pesos. But I think this is very expensive. But considering it is 5 pesos, okay, per gallon of water multiplied by 84 or 81, it should now be 420. So the total cost will be 5,955 pesos. not yet considering the price of the electricity and the labor. Let's go to problem number 2. So we already have here the dimensions. So as we can see, this footing has a dimension of 1.8 by 1.8. So do not be confused. This should be 1.8 by 1.8. Okay, you should base your dimensions on what is specified here. This is not really rectangle but a square because that is 1.8 by 1.8. Okay, how about your column? Your column will be 0.5 by 0.5. So this is a square column also. But the beam, this will now be 0.30 or 0.3 meters by 0.45 meters. And we also have the spacing. Okay, this is 6.5 meters OC. What is the meaning of OC? That is on center. So 4.5 meters on center. Okay, so let us try to estimate again the quantity of cement, sand, and gravel. That should be ordered, or that should be prepared in making this amount of concrete. But first, we should compute the volume of each member. So we will start with footing. Okay, so the footing will now have 1.8 times 1.8 times 0.5. Okay, because that is the proportion. Okay, 1.8. How can we draw that? 1.8 by 1.8. Of course, the length and the width is 1.8. Okay, this should be the figure for your footing. And this right here will be half a meter or 0.5 meters. Okay, therefore the volume will now be multiplied by 4 because the footing has, or there are four footings in this structural frame right here. So multiplying that, we will now have 6.48 cubic meters. How about the column? The column has a specific height of 4.5 meters. Okay, so the column will now be 0.5 by 0.5 times 4.5 meters. We will multiply that also by 4. Okay, because there are 4 columns here in this structural frame. So that will now be 4.5 cubic meters. So now let us estimate the concrete or the quantity of concrete in the beam. So this will now be 0.3 times 0.5, okay, because that is the dimension of your beam. This should be roof of beam. This should be beam of roof. Okay, this should be beam. Okay, beam of roof, or we can also call that roof beam. Okay, 0.3 by 0.45 multiplied by the total length of this beam right here. How can we estimate the total length? That will only be 6 plus 6. Okay, that is 6. Okay, this is 6. This beam right here is 6 meters. 6 meters. Okay, this will be 4 meters and 4 meters. But the dimensions that are written here is 6.5 by 4.5. How is that it is only multiplied by 6, 6, 4, and 4? So let us try to see this in another angle. So for example, this is the top view. 6.5 meters is only measured on the center. Okay, this is measured on the center to center. That is the center of your column. Let us try to go back. That is on center, but it is measured on the column. Therefore, this is 0.25. Okay, this 0.25 should be drawn right here. Okay, this is 0.25. Okay, and this will also be 0.25. Why is it that the half of the dimension of this column right here is 0.25? It is because the column has a dimension of 0.5 by 0.5. Okay, that is the cross section of your column. Therefore, that will now be 0.5 on center and 0.5 on center. But we are just measuring this beam right here. Okay, we are just measuring this length of beam. That is why it is 6 meters. Okay, that is simply 6.5 minus 0.25 minus 0.25. Therefore, it is 6 meters. Same as true with this side of the beam. It is only 4 meters because you will deduct 0.5 and 0.5. Therefore, the dimensions that are used, okay, is 6, 6, okay, 6, 6, 4, and 4. We already have computed for the volume of concrete. It is now time to estimate how much water, cement, and sand should be prepared. Okay, so the total amount in cubic meters of concrete will be 13.68 cubic meters. So it will be simply multiplication. So 13.68 times 9 bags, because we are using class A concrete. Okay, and it will have a total of 123.12 bags. Okay, I think you should round that up. That should be 124 bags of cement. Okay, so the number of sand, you will just multiply the quantity in volume to 0.5 cubic meters of sand per cubic meter of concrete. Therefore, you will need 7 cubic meters of sand. Okay, and gravel, you just multiply that by 1. So for every 13.68 cubic meter of concrete, you will also need 13.68 cubic meter of gravel. And volume of water, you will simply multiply that by 6 gallons. Okay, so that will be, it should be 124 times 6. 124 times 6, that will now be 762 gallons. But sometimes in the construction of the footing, most especially when you are putting it above the soil, they are also requiring a 50 millimeter thick gravel to the bottom, and that will be where they will place your footing. So we can also estimate the additional gravel that is put in the bottom of the footing. So the additional gravel will be 1.8 by 1.8 times 0.05. Okay, this is the conversion of 50 millimeters to meters. Okay, 1.8 times 1.8 times 0.5, because that is how thick. Okay, that is 50 millimeters. It is measured from top to bottom. This is 50 millimeters. Therefore, we should also compute this additional gravel. So 50 millimeters times 1.8 times 1.8, that will be additional 648 cubic or 0.648 cubic meters gravel. And you will just add that up to the total gravel that you have estimated a while ago. So that is how you can estimate the materials that you needed to prepare to make a specified amount of concrete.